Welcome to the new video. In this video, we will solve competitive questions based on moving charges and magnetism. In this question, we are asked to find out the equation of locus of zero magnetic field due to two wires which are perpendicular to each other. This is wire PQ carrying current I1 and wire RS carrying current I2. So due to these two wires carrying current in different directions, which are perpendicular to each other, what is the equation of locus for which the magnetic field will be equal to 0? For the magnetic field to be equal to 0, the magnetic field strength should be equal and opposite. Due to wire 1, the current carrying is I1, and at any point on the coordinate axis xy plane, the magnetic field due to this wire I1 will be B1, and due to wire I2, the magnetic field at the same point on xy plane will be B2. Now if we take the direction of magnetic field at this point, it will be outwards due to wire PQ. Using right hand thumb rule, the magnetic field at this point will be outwards, and due to wire I2, magnetic field at this point will be inwards. So equal and opposite magnetic fields will lead to the magnetic field strength to be 0. Substituting the equation for magnetic field due to infinite wires, which is mu naught I divided by 2 pi r, and distance of this point from the wire PQ is y, and distance of this point from wire RS is x. So mu naught I1 by 2 pi y equal to mu naught I2 divided by 2 pi x. Mu naught by 2 pi, mu naught by 2 pi will get cancelled. The next step is I1 by y is equal to I2 by x. Substituting or simplifying, if we are asked to calculate the equation of locus, so that means we are relating the coordinates x and y. So y will be equal to, taking cross multiplication, y will be equal to I1 by I2 into x. So this is the equation of locus of zero magnetic field. In this competitive examination question, you are asked to calculate magnetic field at point P due to two current carrying wires I1 and I2 which are perpendicular to each other. Point P is at a distance 4 cm from the wire carrying current I1, and point P is at a distance 3 cm from the wire I2, wire carrying current I2, which is with the magnitudes of currents are 2 ampere and 1.5 ampere. At point P, first let us check the directions of magnetic field. The direction of magnetic field using right hand thumb rule due to both the wires is inwards. So the net magnetic field will be B1 plus B2. Magnetic field due to infinite wire is given by mu naught I divided by 2 pi r. You need to remember the equation to solve further. And the value of mu naught is 4 pi into 10 to the power minus 7. Equation substituting the values of I1 and R1, B1 is equal to mu naught I1 upon 2 pi R1 plus mu naught I2 upon 2 pi R2. Solving mu naught by 2 pi, we will get 2 into 10 to the power minus 7, because mu naught value is 4 pi into 10 raised to minus 7. 4 pi divided by 2 pi, 2 pi will get cancelled. You will be left with 2 into 10 raised to minus 7. I1 is 2 and R1 is 4. So I1 by R1 will be 2 by 4, and I2 is 1.5 and R2 is 3. So simplifying this, 2 by 4 is 1 by 2, 1.5 by 3 is 1 by 2. So 1 by 2 plus 1 by 2 will be 1. 1 into 2 into 10 to the power minus 7. So final magnetic field strength due to both the wires simplified together is 2 into 10 to the power minus 7 Tesla. In this competitive question, if the current is carrying in a square loop, the magnetic field has to be calculated at the center of the square, where the side of square is, or edge length of square is A. Let us assume one edge length as a finite wire. Magnetic field due to a finite wire is given by mu naught I by 4 pi r into sine theta 1 plus sine theta 2. We have 4 lengths or 4 sides of a square, so therefore magnetic field at the center due to all the 4 edges is 4 times magnetic field of one side. and magnetic field. First we are supposed to calculate what is the angle subtended. The angle subtended by the corners of square is 45 degree. The angle subtended by the corners of each side is 45 degrees. So the substituting sin theta 1 as sin 45 and sin theta 2 as sin 45, which is 1 by root 2 and 1 by root 2. The distance, edge length or distance of the, if we take the distance from the center, it will be a upon 2. So mu naught I by 4 pi into a upon 2. Simplifying the further expression, we are going to get 2 root 2 mu naught I upon pi into a. We are solving the equation based on the options given in the question. We are seeing in this question based on magnetic field at the center due to two circular current carrying arcs. The first arc has a radius A and the second arc has a radius B, which are having common center O, and current is carried in the clockwise direction. If the current is carried in clockwise direction, the sign convention is magnetic field is inwards. So therefore net magnetic field at the center will be magnetic field due to the first arc plus magnetic field due to the second arc, which is in inwards. Magnetic field due to the circle is mu naught I by 2r. Magnetic field due to semicircle is mu naught I by 4r. Magnetic field due to a quarter is mu naught I by 8r. So this is the this is a quarter, which is magnetic field due to a quarter is mu naught I by 8r, where my radius of the arc is b, therefore it will be mu naught I by 8b. And magnetic field due to the 3/4. 3/4 is nothing but 3 quarter. So it will be 3 into 1 by 8, which is 3 by 8 into mu naught I by 8. Therefore, net magnetic field at the center will be 3 mu naught I by 8a plus mu naught I by 8b inwards. It is a composite of semi-infinite wire and a semicircular arc, where the current flowing in semicircular arc is in anti-clockwise direction. Magnetic field has to be calculated at the center of the semicircular arc due to both the wires. This is a semi-infinite wire and this is a semicircular arc. If the current flowing in the semicircular arc is anti-clockwise, magnetic field at this point will be outwards. Even if we apply Fleming's right hand thumb rule, the magnetic field at this point due to this wire will be outwards. Net magnetic field is B1 plus B2. The current flowing in both the wires is same. Therefore, magnetic field due to semi-infinite wire is mu naught I upon 4 pi r, and magnetic field due to the semicircle is mu naught I by 4r. Taking common mu naught I by 4r, we are left with 1 by pi plus 1 mu naught I by 4r. Taking LCM, it will be pi plus 1 upon pi. Finally, taking out the term pi, my net magnetic field at the center due to both the wires is mu naught I by 4 pi r into pi plus 1. Circular coil carrying current I. We are asked to calculate when will the magnetic field be 1/8 its magnetic field at the center. I repeat, we have magnetic field at the center due to current carrying coil, which is I, which is maximum. Current carrying magnetic field is maximum at the center due to the current carrying coil. At what point on the axis will the magnetic field be 1/8 its time at the magnetic field due to center? The equation is given by B center upon B axis, which is equal to 1 plus x square upon r square to the power 3 by 2. Here in the question they have specified the radius of the coil is A. Substituting B center is, let us take the magnetic field at B center is BC, and magnetic field at axis given as 1/8, so 1/8 of BC, 1 plus x square upon a square to the power 3 by 2. BC get cancelled, 8 will go to the numerator, it will become 8. 3 by 2 shift the power towards this side, it will be 8 to the power 2 by 3. 8 I can write it as 2 cube, so 3 will get cancelled, 2 square, which will be equal to 4. 4 equal to 1 plus x square upon a square. X square upon a square is equal to, shift 1 towards this side, it will become 3. X square is equal to 3, a square x will be equal to root 3. At a distance root 3 times its radius, magnetic field will be 1/8. In this question, we are asked to calculate magnetic field at the center due to a circular loop, where we know the expression, which is mu naught I upon 2r. But the options given are in terms of epsilon, not in terms of mu naught. So the radius of circular loop given as 5 centimeter, we can convert it into its SI units, which is 5 into 10 raised to minus 2, and current given is 0.9 ampere, mu naught I upon 2r. So relation between mu naught and speed of light from the chapter electromagnetic waves is speed of light c is equal to 1 by square root of mu naught into epsilon. Squaring this, we'll have c square is equal to 1 by mu naught into epsilon. To substitute mu naught, we'll cross multiply, we'll have mu naught equal to 1 by c square into epsilon. Substituting, In the equation, magnetic field at the center, which is mu naught I by 2r, mu naught value we have calculated and we have got it as 1 by c square into epsilon, 1 by c square into epsilon. Current value, current flowing in the circular loop is given as 0.9 ampere, substitute 0.9 ampere, and it is 2r. So the radius of circular loop is 5 centimeter, converted, which is 2 into 5 into 10 raised to minus 2. Simplification, c square, speed of light is 3 into 10 raised to 8, squaring it, 3 square is 9, 10 to the power 8 square is 10 to the power 16, so 9 into 10 to the power 16 into epsilon, into 2 into 5 will be 10, 10 into 10 raised to minus 2 will be 10 raised to minus 1, 10 raised to minus 1 taking to the numerator, it will be 10 raised to plus 1, 0.9 into 10 raised to plus 1 is 9, 9 and 9 will get cancelled, we are left with 1 by 10 raised to 16 epsilon, where first option is the right answer. The hack in the question is speed of light c is equal to 1 by root of mu naught into epsilon.